Hi, my name is Brian Caffo, and welcome to the lecture on asymptotics as part of the Statistical Inference class in the Coursera Data Science Specialization. This class is co-taught by my co-instructors Jeff Leake and Roger Peng, who are all at the Johns Hopkins Bloomberg School of Public Health. So asymptotics is the term for the behavior of statistics as the sample size, or some other relevant quantity, limits to infinity, or in some cases as something else limits to zero. We're going to deal only with the case where the sample size is the quantity that's limiting to infinity. Asymptopia is my name for the land of asymptotics, where everything works out well, and it should work out well because there's an infinite amount of data in the land of asymptopia. So asymptotics are incredibly useful for simple statistical inference and approximations. Asymptotics are like a little Swiss Army knife that you can pull out to investigate the statistical properties of many statistics without having to do much computing. So not covered in this class is that asymptotics often lead to nice understandings of procedures. However, asymptotics generally give no assurances about finite sample performance. They only talk about the performance as the amount of data limits to infinity. So asymptotics also form the basis for frequency interpretation of probabilities. For example, everyone kind of intuitively knows that if you flip a coin and take the proportion of heads, that should limit to 0.5 for a fair coin. That property is the so-called law of large numbers that we'll explore here in a minute. Fortunately, instead of diving into the mathematics of the limits of random variables, there's a set of powerful tools that we can rely on. These results allow us to talk about the large sample distribution and behavior of sample means of a collection of IID observations. The first of these we already intuitively know, the so-called law of large numbers. It says that the average limits to what it's estimating, the population means. So for example, the average could be the result of n coin flips, the sample proportion of heads. As we flip a fair coin over and over, it eventually converges to the true probability of a head. Let's show the law of large numbers in action. I'm going to set my number of simulations to be 1,000. Then I'm going to generate 1,000 random normals, and I'm going to take their cumulative sum. Then dividing the cumulative sums by 1 over n gives the cumulative means. In other words, the mean of the first observation by itself, then the mean of the first and the second observation, then the mean of the first, second, and third observation, and so on. What you see when you plot the cumulative means by the index is early on there's a lot of variability in the mean, but then as time goes on, not as time, as the number of simulation goes on, we get closer and closer to the true population value, which is 0. Let's do it again, only this time let's ask R to flip a coin rather than generate standard normals. So the function sample, when I give it the arguments 0 and 1, samples from the elements 0 and 1 with equal probability. Here I want n of them, 1,000, and replace equals true just means that I want to sample with replacement. So this command is exactly flipping a coin 1,000 times, where 0 is a tail and 1 is a head. I'm taking again the cumulative sum and then dividing it by 1 to n to get the cumulative means. When I plot the cumulative means, what I see again is variability in the sample proportion early on, but as the number of coin flips going into the sample proportion goes to infinity, it converges to the true value, which is 0.5, which is right there. Let's have a brief discussion. We define an estimator as consistent if it converges to what you want to estimate. So for example, the sample proportion from IID coin flips is consistent for the true success probability of a coin. As you flip a coin over and over, the sample proportion of heads converges to the probability of getting a head on that coin. The law of large numbers says that the sample mean of IID samples is consistent for the population mean. This is a very good property to have, because it's basically saying if we go to the trouble of collecting an infinite amount of data, we get exactly the right answer. But it's not only true that sample means are consistent, the sample variance and the sample standard deviation of IID random variables are consistent as well. Perhaps the most important theorem in all of statistics is the so-called central limit theorem. For our purposes, the central limit theorem states that the distribution of averages of IID random variables becomes that of a standard normal as the sample size increases. Because it has fairly loose requirements on the collection of populations that it applies to, the central limit theorem applies in a nearly endless variety of settings, and we'll go through several. The basic result is that if we take an estimate, like the sample average, x bar, subtract off its population mean, mu, and divide by its standard error, sigma over square root n, that random variable limits to that of a standard normal. I would also add that replacing the population standard deviation, which is unknown, by the sample standard deviation, which is known, does not change the central limit theorem. The most useful way we think about the central limit theorem is to say that the sample average is approximately normally distributed with a mean given by the population mean and a variance given by the standard error of the mean. So let's go through several examples to illustrate the central limit theorem using simulation. First, let's start with a standard die. What's interesting about this conceptual experiment and the simulation that we're going to conduct is that imagine if you had to simulate random normals prior to the advent of computers. For example, if you were a statistician working at that time and you wanted to evaluate the behavior of something like the chi-squared statistic, which is a function of normal random variables. So let's let xi be the outcome for die I, and remember that the mean of the distribution of die rolls is 3.5 and that its variance is 2.92. So the standard error of the mean is square root 2.92 over n. Let's roll n dice, take their mean, subtract off 3.5, and divide by 1.71 over square root n. And repeat this over and over again. If the central limit theorem is right, this should look exactly like a standard bell curve. So just to remind ourselves what's happening, we rolled the dice 10 times in this first panel, we subtracted off 3.5, and we divided by 1.71 divided by square root 10. We repeated that process over and over and over again, and the histogram displays the distribution of the different normalized averages that we got. We know already that this distribution has to be centered around 0 because we've subtracted off the mean 3.5, so it has to be centered around 0. And we know exactly what the variance of this distribution has to be were we to repeat this process infinitely many times. However, what the central limit theorem is telling us is also the shape, and the shape has to be like that of a bell curve, and because we normalize the data, it has to be exactly that of a standard normal. And we see that the approximation is actually very good, even for just 10 die rolls. For 20 it gets even better, and for 30 it's better still. Flipping a coin is an interesting case because it goes back to the original development of the central limit theorem as an approximation for the distribution of sample proportions. So let's let xi be the 0-1 result of the I flip of a possibly unfair coin. Then recall we usually give the notation p hat as the sample proportion, which is simply the mean or the average, the empirical average of the coin flips coding 0 as a tail and 1 as a head. Recall that the expected value of xi is p, and that the variance of xi is p times 1 minus p. Then the standard error of the mean, or the standard error of the proportion of heads, p hat, is square root p times 1 minus p over n. So if we take the statistic p hat, subtract off its population mean, and divide by its standard error, square root p times 1 minus p over n, that should be approximately normally distributed if n is large enough. Now notice if the coin is fair, then p is 1/2, and p times 1 minus p is a quarter, which as a square root is 1/2. So the standard error for a fair coin flip is 1 over 2 square root n. So let's flip the coin n times, take the sample proportion of heads, subtract off 0.5, and multiply the result by 2 square root n. Here's the result of our simulations. Consider the panel with 10 coin flips here on the left. This is the result of flipping the coin 10 times, subtracting off the population mean, 0.5, and dividing by the standard error of the mean, square root p times 1 minus p over n. Doing this over and over and over again, we get a good sense for what the distribution of normalized proportions of 10 coin flips looks like. It's centered at 0 because we subtracted off the mean, and its variance is governed by the p times 1 minus p over n. What this lecture is telling us is that the distribution should be approximately that of a standard normal. And for reference, I drew the density of the standard normal here. You can see some of the discreteness. There's only 2 levels for a coin, so the average of 10 coin flips can only take so many different combinations, and so some of the discreteness is showing through. But when we get to 20 or 30 coin flips, we can see that it actually looks quite Gaussian. I would like to emphasize that the speed at which the normalized coin flips converges to normality is governed by how biased the coin is. For example, here I show what the simulations look like for a probability of head of 0.9. You can see for 10, that distribution does not look very bell-shaped. By 30, it's getting there, but still the probabilities, when approximated by the normal distribution, would not be perfect. So just keep this in mind, that the central limit theorem doesn't guarantee that the normal distribution will be a good approximation. Simply that as the number of coin flips limits to infinity, eventually it will be a good approximation. As a fun aside, I wanted to talk about Galton's quincunx, a machine that you might have seen if you visited a science museum. Basically, the crux of this machine is illustrating the central limit theorem with a game that looks a little like pachinko. So here's an example. What would happen is a ball would come down here, and it would fall down here, and it would hit this peg, and then it would go left or right with equal probability. And then it would go down, let's say it went in this direction, and then it went down there, and then it would fall left or right with equal probability. And eventually the ball would work its way down to a bin, and it would get collected down here. You can think of each time the ball hits a peg and has to choose left or right as a binomial experiment, a coin flip. If it were to get all successes, let's say, it would head all the way over in this direction. If it were to get all failures, it would head all the way over in that direction. It would be like flipping a coin. So each row is like another coin flip. By virtue of the central limit theorem, we know that the proportion of heads from a bunch of coin flips is approximately normally distributed. So we could multiply that by n and then also conclude that the sum, the total number of heads, will also be approximately normally distributed. And so what you'll see at the Science Museum is that the balls will collect down here, and they'll actually draw the relevant normal distribution right there. And you'll see as the balls collect, they'll collect up into this and exactly overlay this superimposed normal distribution, and then when it fills up to that point, there's usually a little thing that drops all the balls down and it starts over again. So at any rate, it's a fun idea. You can Google online and see some examples of Galton's quincunx. It's a fun application of the central limit theorem. So let's develop a more practical use of the central limit theorem. Recall that the sample mean is approximately normally distributed with population mean equal to mu and standard deviation equal to the standard error of the mean sigma over square root n. In this distribution, mu plus 2 standard errors is pretty far out in the tail, with only a 2.5% chance of a normal being larger than 2 standard deviations into the tail. Similarly, mu minus 2 standard errors is pretty far in the left tail, with only a 2.5% chance of a normal being smaller than 2 standard deviations into the left tail. So the probability that x bar is bigger than mu plus 2 standard errors or smaller than mu minus 2 standard errors is 5%. Or equivalently, the probability that mu is between these limits is 95%. We can reverse the role of x bar and mu without changing the probability inequalities and get that the quantity x bar plus or minus 2 standard errors contains mu with probability 95%. Remember here that we're treating the interval as random, x bar plus or minus 2 standard errors, while mu is fixed. So we talk about the probability that the interval contains mu. The actual interpretation of this is that if we were to repeatedly get samples of size n from this population, construct the confidence interval in each case, about 95% of the intervals we obtained would contain mu, the parameter that we're trying to estimate. I would note that I get the 2 by rounding up the 97.5th quantile, which is closer to 1.96. If you wanted a 90% interval, what you need is 5% in either tail. so you would replace the 2 with 1.645. Let's go through a simple example. Consider the father.son data from the using R package. Define x to be the son's height. I'm simply going to take mean of x plus or minus the 0.975th normal quantile times the standard error of the mean, standard deviation of x divided by the square root of n, which is the length of the vector x. I divide it by 12 so that my confidence interval will be in feet rather than inches, and I get the confidence interval 5.710 to 5.738. So if we were willing to assume that the sons from this data were an IID draw from a population of interest, then the confidence interval for the average height of the sons would be 5.71 to 5.74. Let's consider coin flips and developing a confidence interval for the success probability of the coin. So in this case, each observation xi is a 0 or 1 with a common success probability p, and remember the variance of a coin flip was p times 1 minus p, where again p is the true success probability of the coin. Remember then the standard error of the mean is square root p times 1 minus p over n. So the interval takes the form p hat plus or minus the normal quantile times square root p times 1 minus p over n. We don't know p, it's what we want to estimate, and so we don't have this standard error, but we would replace it by p hat. And this is a confidence interval that is called the Wald confidence interval, named after the great statistician Wald. It turns out p times 1 minus p is as large as it can be when p equals a half, so that square root p times 1 minus p is 1/2, and when we multiply it times the 2 in the 95% interval, those cancel out, and we get that for 95% intervals, p hat plus or minus 1 over square root n is a very quick confidence interval estimate for p. Imagine you were running for political office and your campaign advisor told you that in a random sample of 100 likely voters, 56 intended to vote for you. Can you relax? Do you have this race in the bag? Is 0.56 out of 100 sampled enough evidence to conclude that you will likely get more than 50% of the vote? But you don't have access to a computer or calculator. So what you do is you do 1 over square root 100, which yields 0.1. So the back of the envelope calculation gives an approximate 95% interval of 0.46 to 0.66. The confidence interval says that we can't rule out possibilities below 0.5 with 95% confidence. So not enough for you to relax, and you better go do more campaigning. So some general rough guidelines is that you need 100 for 1 decimal place in a binomial experiment, 10,000 for 2, and 1,000,000 for 3. Here I just give 1 over the square root of a bunch of powers of 10 just to illustrate that. Here I just go through the calculation where I plug 0.56 directly into the standard error formula. So we have 0.56 plus or minus the relevant standard normal quantile times square root 0.56 times 0.44 over 100. This yields the interval 0.46 to 0.66, just like before. Also, the function binom.test with 56 successes out of 100 trials and grabbing the confidence interval component yields a very similar interval, 0.46 to 0.66. The binom.test function is exact in the sense that it yields 95% coverage or higher regardless of the size n. These so-called exact procedures are a nice complement to large sample procedures. They tend to involve computations that cannot be done by hand and can be conservative, i.e. have wider intervals, but nonetheless they do not rely on the central limit theorem. Let's consider a simulation. Here I'm going to do a simulation where I flip a coin with a given success probability over and over and over again and calculate the percentage of times my Wald interval covers the true coin probability that we used to generate the data. So I'm going to say in each one of my simulations I'm going to do 20 coin flips. The true values of the success probability of the coin that I'd like to look at vary between 0.1 and 0.9, where I step through them by values 0.05. I'm going to do 1,000 simulations. And then I'm going to loop over these true success probabilities, and for each true success probability, I'm going to generate 1,000 sets of 10 coin flips where I take the sample proportion in each case. Then I'm going to calculate the lower limit of the confidence interval in each of those cases and the upper limit of the confidence interval in each of those cases, and I'm going to calculate the proportion of times that they can cover that true value of p that I used to simulate the data. This will all be in this variable that I'm calling coverage. Now what I'd like to do is plot coverage as a function of the true success probability I used to simulate the data. Here I show the plot of the coverage by the true values of p used for simulation. So for example, at the value 0.5, I flipped the coin 10 times, took the sample proportion, found the confidence interval, and then gave it a 1 if it covered the value 0.5 or not. I did that 1,000 times, and in this case, over 95% of the time, it did in fact cover that probability. So it's basically saying if the true value of p was 0.5 and I do a confidence interval, the coverage is actually better than 95% a little bit. There is some Monte Carlo error, right, in that I didn't do an infinite number of simulations. I only did 1,000. But 1,000 is pretty good, right? As we saw in a couple slides ago, it's giving us a little bit better than 1 decimal place accuracy. Now, here, it's pretty clear that I'm getting nowhere near 95% confidence level for the case where the p is around here, around 12% or so. Now, why is this the case? Why is it that a 95% confidence interval procedure is clearly giving us coverage less than 95%? And it's simply because the central limit theorem isn't as accurate as we need it to be for this specific value of n for coins with this specific true probability. So I'll give you a quick fix to address this problem for smaller values of n. The quick fix is to simply take your number of successes, x, and add 2, and your number of failures, and also add 2, so that your p hat is now x plus 2 over n plus 4. So adding 2 successes and failures. Then you just churn through the confidence interval procedure as normal, but with this new sample proportion that's been shrunk towards 0.5 a little bit. This is called the Agresti-Cool interval, and in a minute we'll show you how it performs a little bit better. Before I show the results for adding 2 successes and adding 2 failures, I want to simply show that the performance is better when n is larger. Here I've done exactly the same simulation, but turned n into 100 rather than 20. And here you see the coverage probability as a function of the different values of p. Only now the only difference is that within each confidence interval that I simulated, I used a greater number of coin flips. So in each case, take for example this point right here. For that specific true value of p, I simulated 100 coin flips, took the sample proportion, created the confidence interval, and saw if it contained this true value of p. And over 95% of the instances, that was the case. You see, here's the 95% line right here, and you see that the coverage probability is fairly close to it throughout. It never dips below 90 like it did in the 20 case. Now let's look back at the 20 case again. So I'm setting n equal to 20, okay? But now, when I calculate my confidence interval here, notice that I am adding 2 successes and 2 failures. So let's see the performance of that. And you can see that the add 2 successes and add 2 failures interval tends to cover the true success probability with a higher percentage of time than 95%. This is a little bit better than the extremely poor coverage of the walled interval for certain values of the true probability. However, being too conservative, in other words, having too high of a coverage rate, is also not necessarily a good thing, as it implies that the interval is probably too wide. Nonetheless, I've done some thinking about this specific problem, and I can give a very categorical recommendation that the add 2 successes and add 2 failures interval should generally be used instead of the walled interval. Let's create a Poisson interval using the estimate plus or minus normal quantile standard error of an estimate formula. This is based on the central limit theorem, though it's maybe a little less clear how the central limit theorem is applying in this case. I'll talk about that a little bit in a minute. So let's talk about a nuclear pump that failed 5 times out of 94.32 days. Give a 95% confidence interval for the failure rate per day. So I'm going to assume that my number of failures is Poisson with failure rate lambda and t being the number of days. So my estimate of the failure rate is the number of failures divided by the total monitoring time. The variance of this estimate turns out to be lambda over t, so that lambda hat over t is our empirical variance estimate. Here I just go through the calculations in R. I define my number of events here as x being 5. The monitoring time is 94.32. My estimate of the rate as x over t, and my confidence interval estimate as the rate estimate plus or minus the relevant standard normal quantile times the standard error. And then I round it so that I only get 3 decimal place accuracy. So here is my estimate for the rate, my 95% confidence interval estimate for the rate. In addition to doing a large sample interval, we can do an exact Poisson interval, and R has a function for doing it. It's Poisson.test. We give it the number of events and the monitoring time, and then you can just grab the confidence interval part of it, and there it gives the exact Poisson interval. What I mean by exact here, again, is that it guarantees the coverage. But that might be conservative. It might give you a wider interval than necessary, but it will guarantee 95% coverage. Just because we're very interested in seeing how confidence intervals perform on repeated sampling, since that defines our idea of what a confidence interval is, let's repeat the process that we did for the coin for the Poisson coverage rate. So let's pick a set of lambda values kind of near the ones from our example. Let's do 1,000 simulations. Let's set our monitoring time as 100 instead of 94 just to make it simple. And then I'm going to define coverage in the same way. I'm going to simulate a bunch of Poissons with this particular rate, and then I'm going to divide it by the monitoring time to get a vector of lambda hats over 1,000 simulations. I'm then going to create my 95% confidence interval by constructing the lower limit, where I subtract off the standard normal quantile times the standard error, and then a bunch of upper limits where I add the standard normal quantile times the standard error, and then I'm going to take the percentage of times that my interval contains the true lambda used for simulation, and I'm going to do that over a series of lambda values, and then in the next slide I'm going to show you the plot of the lambda values by the Monte Carlo estimated coverage. So here's the plot of our lambda values by the coverage. So every point in this plot is an instance where we simulated and repeatedly generated Poisson confidence intervals and took the percentage of time that those intervals contained the true lambda value used for the simulation. We can see as the lambda values get larger, the coverage gets closer to 95%. There is, of course, some Monte Carlo error because we didn't do an infinite number of simulations, only 1,000. We also see that as the true value of lambda gets smaller, the coverage gets very poor, and you probably can't see this number terribly well here, so I'll zoom in. That coverage is 50% right there. So your purported 95% interval is only giving you 50% actual coverage. So our brief simulation here is suggesting that for very small values of lambda, which we have a good sense of if we have relatively few events for a large amount of monitoring time, for relatively small values of lambda, we shouldn't be using this asymptotic interval. Since it's not immediately clear how the central limit theorem works in the Poisson case, I just wanted to put up one simulation to show that what's going to infinity to make the Poisson case have very good approximations using the central limit theorem. And basically, as the monitoring time goes to infinity, the coverage will converge to 95%. So in this simulation, I changed t from 100 to 1,000 so that we're monitoring not for a total of 94.32 days, but a total monitoring time of 1,000 days. And here we see that the coverage, if we look at the reference line here at 95%, the coverage is much much, much better for most values of lambda. There is some poor coverage down here near the smaller values of lambda, but we know that this interval has problems with small values of lambda. But remember, in this case, we do have the exact Poisson interval as an option. So congratulations on making it through this marathon lecture. Because there was so much content, I'd like to summarize very briefly. First of all, we covered the law of large numbers, and that simply states that averages of IID random variables converges to the things that they're estimating. I would also add that it also shows that Poisson rates converge to the rates that they're estimating, though it's maybe a little less clear how that works, but as the monitoring time goes to infinity, for example. The central limit theorem is also a theorem involving averages, and it states that averages are approximately normal with distributions centered at the population mean, which we knew regardless of the central limit theorem, and with standard deviations equal to the standard error of the mean, which we also already knew without the central limit theorem. However, the central limit theorem also tells us that they're approximately normal. However, the central limit theorem doesn't give any guarantee that n is large enough for this approximation to be accurate, and we've seen some instances with confidence intervals where it's very accurate and instances where it's less accurate. Speaking of confidence intervals, taking the mean and adding and subtracting the relevant normal quantile times the standard error yields a confidence interval for the mean. And this process of estimate plus or minus some sort of quantile times the standard error is our default way for creating confidence intervals, whether it's in this context or in our regression class, or even when we're talking about generalized linear models and more complex subjects, we tend to use these so-called walled intervals. The specific case where we want a 95% confidence interval, you can take 2 as the quantile, or if you want to be a little bit more accurate, use 1.96. Now, confidence intervals get wider as the coverage increases if you're staying within a single technique. Now, why would this be the case? So imagine if someone were to put a gun to your head and say, unless this confidence interval contains the true parameter it's estimating, I'm going to pull the trigger, which is a ridiculous circumstance, but humor me. What would you do? Well, you certainly don't want them to pull the trigger, right? So what you would do is you'd make the confidence interval as wide as you possibly could, because you want to be very sure that the interval contains the parameter. So that's the same thing that the mathematics does. The more sure you want the more sure that you want to be that the interval will contain the parameter, the wider the procedure makes the interval. If you don't care at all, if you want a 2% confidence interval, then you're going to have an interval that's very close to the mean itself. Now, the Poisson and binomial cases are discrete cases, and we saw that the central limit theorem can sometimes not approximate their distributions well, and in those cases there are exact procedures. But we also saw a simple fix for the binomial case if you're creating confidence intervals, where if you add 2 successes and you add 2 failures, you get a much better confidence interval without much extra thinking or having to resort to something that requires a computer. So you can still do that calculation by hand if you happen to be, or in your head if you happen to be not around a computer.